So, hello everyone. Today I'm going to present the second session of the Introduction to Deep Generative Model, where I'm going to talk about latent variable models with a focus on variational autoencoders and normalizing flows. To recap the previous session, Fatima talked about generative models and the uses of generative models. So, for example, for some generative models, we can perform density estimation. And with density estimation, one can perform other tasks such as outlier detection. Since it is a generative model, we can do data generation by sampling from the model. And also with some generative models, we can do representation learning. Fatima also talked about autoregressive models, which is a likelihood-based generative model that tries to learn the joint probability distribution based on the chain rule. It is a perfect choice for sequential data as it models each time step based on the previously generated or modeled data, and it is trained with maximum likelihood. Autoregressive models are really powerful and simple and efficient to train if we use, for example, tricks like causal convolutions. And it is good during training because no sampling is required during training, so it can be done efficiently. However, autoregressive models are slow at generation time because of that autoregressive component. And since it doesn't map the data into a latent space, it cannot be used for unsupervised representation learning. What we will talk about today is latent variable models, or LVMs. Similar to autoregressive models, LVMs are likelihood-based generative models, but compared to autoregressive, they take a different approach to model the joint distribution. They do it by using an unobserved latent variable. For example, we call it Z in this presentation. And a latent variable is used to explain the observation, so it can be a good way of unsupervised representation learning. And we can also generate data points given the latent variable. And LVMs first start with the latent variable and then define a transformation that maps the latent variable configuration to some particular observation. Similar to autoregressive models, LVMs are also trained with maximum likelihood. And in some cases that we will see during this presentation, we use some approximation to maximum likelihood because it is often is not tractable. LVMs are pretty powerful, and sampling from LVMs is very efficient because unlike autoregressive models, we do not have any sequential component, autoregressive component, and it is well suited for representation learning because we use the latent space. But on the other hand, these class of generative models are more complex compared to fully observed models. The latent-based models are conceptually more complex. And it is not easy to use the exact inference. So sometimes we need to use approximate inference, which we will see in VAEs. Or if we want the exact inference, we need to restrict our model to be able to do so, which again, we will see in normalizing flows. So let's get into an introduction to latent variable models. So latent variable models define a distribution over the observations in our dataset by introducing a latent variable Z. And in order to use this latent variable Z, we need to define two distributions. One is the prior distribution, P of Z, that can be a very simple distribution, like the normal distribution, and the likelihood, P of X given Z. And the likelihood, P of X given Z, essentially tells us the mapping from the latent configuration Z to a data point X. And once we have the prior and the likelihood, we have specified the model completely. So we can define the joint distribution P of X comma Z which can be computed by multiplying the likelihood by the prior. And there are two other distributions that we can derive from the joint distribution. And these two are of interest to us and are essential for latent variable modeling. The first one is P of X, the marginal likelihood of an observation, which simply tells us how probable an observation is under the model. And this is the quantity that we maximize during training if we use maximum likelihood. The second distribution that we are interested in is P of Z given X, which we call it posterior distribution. And this is the distribution of plausible latent configuration that could have been generated from the observation X. So why latent variables are important? We can think of latent variables as some sort of explanation for the observation. And another aspect of using latent variables is that we can generate a data like the ones that we are seeing in the data set. So how we generate an observation from a latent variable model? It's actually quite simple. We start from sampling a latent variable from the prior distribution. And then we sample from the likelihood distribution. And then that gives us a data X. And the likelihood distribution is a conditional on the configuration of the latent variable that we've sampled from the prior distribution. Another concept that is important in latent variable modeling is inference. And inference is the inverse of the generation process. So instead of going from Z to X, during inference, we go from X to Z. And this is going to be the mapping from the observation X to a latent configuration Z. So inference essentially refers to computing the posterior distribution for a given observation. So we are interested in computing P of Z given X. How it is defined? Well, we use the definition of the conditional probability, which says P of Z given X is the ratio of the joint distribution under the model divided by the marginal probability of X, P of X. This means that in order to compute the posterior distribution, we first need to compute the marginal likelihood. How do we do that? We start from the joint distribution, P of X comma Z, and marginalizing out the latent variable Z. For example, in the case of continuous latent variables, it is done by integration over the configuration of Z, and in the case of discrete latent variable, it will be the summation over all configuration of Z. So why inference is important to us? First, it is important because once we've trained the model, we can use inference to explain the observation in terms of the latent configuration. It allows us to better interpret the observation, and we will see a really nice and simple example when we discuss variational autoencoders. Moreover, as we will see in a bit, inference comes up naturally in maximum likelihood training of the model. It is, in fact, the sub-problem that we need to solve over and over in an inner loop of the training. But the problem is that exact inference is not simple. To see why, let's take a look at the computation of the marginal likelihood of the observation X. So computing this term is intractable because of this integration or the summation in the case of discrete latent variable, we need to consider all possible configuration of Z. And in practice, Z is often high dimensional. So we need a lot of consideration of Z to have a reasonable approximation of P of X, which if we want to do it over and over in the training loop, it is like not possible to scale the model to large data sets. So to avoid intractable inference, we have two options. First, approximating inference, which does not allow us to compute the exact posterior, but in turn, we can use very expressive model to represent the data or to represent the latent variables. The second option is a specific design of the model that allows us to compute the exact inference, which leads to a simpler training because we do not need to approximate the posterior. But our hands are not that open to choose any architecture for the model, as it should have certain properties, as we will see. So the example of the first option is variational autoencoder, and for the second option, we talk about normalizing flows. So in VAEs, we use an encoder and a decoder. Using the encoder, we map the data into a very low dimensional latent space, and then we sample a latent variable from this latent space and use the decoder to generate a data point. Unlike VAEs in normalizing flows, the latent dimension Z is exactly the same as the data dimension. And instead of an encoder and a decoder to connect the data to the latent variables, we use an invertible transformation F. So to go from X to Z, we use F. And to go from Z to X, we use the inverse of the exactly same function. So now let's talk about variational autoencoders. Earlier, we saw that exact inference is hard because to compute this marginal likelihood, we need to consider all configuration of the latent variables. VAE's solution to this is to approximate the posterior instead of computing the true and exact posterior. And this is done by introducing another distribution, Q of Z given X, which is parameterized by phi, showing that, for example, it can be another neural network. And the whole goal is to make a really good approximation of the true posterior. And we call Q the approximate posterior. Here is an overview of variational autoencoders. We would like to model the data distribution, which is complex and unknown. And variational autoencoders does this by using an encoder, a latent space, which we know the parameters of, and a decoder. During training, the encoder tries to map each data point to a region in the latent space. Then we sample from that region of the latent space and use a decoder to map back from the latent space to the data space. And by doing this over and over during training, the encoder learns to map the data to a good region of the latent space, and the decoder learns to generate a data point or reconstruct a data point given a reasonable variable in the latent space. So after training, we can ignore the encoder if we want to generate the data, for example. We can sample from the prior distribution, which we know the parameters of, and use a decoder to generate a sample that looks like the samples that we've seen during training. So let's see what is VAE's objective function. We said it's done by introducing an approximate posterior distribution, which we try to be as close as possible to the true posterior distribution. The natural option to make these two close to each other is by minimizing the KL divergence between these two distributions. Before going to the details, let's have a quick background on KL divergence. KL divergence is a measure of the difference between two distributions, and it can be computed in this form. There are certain properties with KL divergence that are important to us. The first thing is that KL is always non-negative, and it's only zero when the two distributions are exactly the same, and it's non-symmetric. So the KL divergence between Q and P is not necessarily equals to the KL between P and Q. So let's see how we can compute this KL divergence. We can expand the KL divergence of this form into log of Q minus log of P. And we know that this is the true posterior, which can be written in this form using the Bayes theorem. So we can use this formulation instead of log of P of Z given X. And if we do that, we see that P of X is independent of Z, that is the parameter of the expectation, so we can pull it out of the expectation. And then we can put P of X to the left side of this equation, and we have something like this. And then we multiply everything by -1, and we rearrange the right-hand side of the equation. And by doing so, we see that here we have another form of KL divergence. And this time the KL divergence is between the approximate posterior and the prior distribution. So what we end up with is something like this. We have the log likelihood of the data. We have the KL divergence between the approximate and true posterior. We have our likelihood, or we can refer to reconstruction loss. And we have the KL divergence between the approximate posterior and the prior distribution. But we know that the exact posterior, we cannot compute it because it is hard. But according to the definition of the KL divergence, we know that it is always positive. So what we can do is, instead of optimizing the exact log likelihood of the data, we can optimize the lower bound on the data log likelihood, which we call it evidence lower bound. Because if you remember from the first session, we call P of X the evidence. So it is called the evidence lower bound, or in short, ELBO. So this is for the VAEs, and we can simply extend it to conditional VAEs by introducing a conditioning signal C. And every probability distribution that we have in the ELBO are going to be conditioned on C as well, which we won't go into detail of that. So let's see how we can make a variational autoencoder in practice. What we need is a prior distribution, P of Z, which could be as simple as a Gaussian, a normal distribution. Then we need an encoder that maps the data to the latent space. And the latent space can be another Gaussian distribution. And we can simply model the parameters of this distribution, like mu and sigma, using a neural network. And then we have a decoder that maps the latent variable that is sampled from this distribution to the data distribution, which is going to look like this. So the encoder gets as input the input sample from dataset, maps it to the posterior, maps it to the latent space by approximating the posterior distribution parameters by mu and sigma. Then we sample the latent variable from this approximate posterior, pass it to the decoder, and reconstruct the data. But we know that sampling is a stochastic operation, and it's non-differentiable with respect to network parameters. So the solution is to separate the stochastic operation and make it independent of the network parameters. This is called reparameterization trick. How we can do that? It is like sampling an epsilon, a variable epsilon, from the normal distribution, which is completely independent of the network parameters. And then we can shift and scale epsilon given the estimated posterior parameters. So this is equivalent to sampling the latent variable Z directly from the approximate posterior. And at the end, we have the loss functions. As we saw in our ELBO, we have a reconstruction loss and we have a KL divergence loss. The reconstruction is simply the reconstruction loss between the reconstructed output and the input. And the KL divergence we computed between the approximate posterior parameters by mu and sigma and the prior distribution. So since it is a generative model, once we've trained, we can generate new samples. For example, when we train a VAE on images of faces, then at the test time, we can ignore everything up to here. So we can ignore the encoder because we do not have the input data. We can sample Z from the prior distribution and pass it to the decoder and generate new samples. And this is what exactly has been done here. Another important property of variational autoencoders as a latent variable model is that we can use them for representation learning and visualization. For example, here, this is the case of having a 2D latent space that, given a latent variable from this space, we can generate data points. And here we can see what each dimension of the latent space can tell us about the data. For example, here in MNIST digit example, we can see that we have the latent variable describes different styles of writing or different digits. Or in the case of this face generation, we can see that the latent space talks about the facial expression or the orientation of the head. So it is a really nice way of visualizing and interpreting data in an unsupervised manner. And So as we said earlier, with VAEs, we cannot have the exact inference, but in turn, we are allowed to use any expressive architecture for the encoder and decoder. And this work, NVAE, which is pretty recent, 8th of July this year, focuses exactly on the same thing. It talks about what are the best components that we can use to have a very expressive model to generate images that can compete with other likelihood-based generative models. So these results are really impressive with variational autoencoders, which we do not have the exact inference for. Now let's take a look at the other class of generative models that, unlike VAEs, allows us to compute the exact inference. Normalizing flows, which also known as invertible models, allows us to do tractable inference. And the basic idea behind this model is to start from a prior distribution, like other latent variable models, and then apply an invertible function to it to obtain the observation. And by warping the prior distribution through such transformation, we can approximate the data likelihood. So let's take a look at the generative description of an invertible generative model. We need a prior distribution like this, and we need an invertible and differentiable function, f, so we can map every sample from the latent space Z to an observation from the data distribution. And because we use f that is invertible, having this setup gives us the one-to-one correspondence between the latent configuration and the observation. So we know that which latent configuration from this distribution generates some particular observation in the data distribution and vice versa. And this means we can come up with the latent configuration by applying the inverse of f, so we can go from x to z. So we can know what latent configuration could have generated this data point. And this is the interesting thing about normalizing flows and the inverse of f, that the inference computing z given x is pretty easy. So how we do compute the marginal likelihood, p of x? Using the invertible transformation between the prior and the data distribution, p of x, these two distributions only differ by a scaling factor in this form. And based on the change of variable formula, which I will introduce in case you don't know it, it is the scaling factor. This scaling factor is the absolute value of the determinant of the Jacobian of the mapping from z to x. And we know that the determinant is one real number computed as a function of all elements of this Jacobian. And the absolute value of the determinant can be thought as a measure of how much this multiplication by this scaling factor expand or contrast the original space P of z. This might be surprising where this factor comes from, which I will describe in a bit. But simply, this factor simply accounts for the fact that when we apply a function to go from z to x, or vice versa from x to z, it will change the infinitesimal volume around the point it's being applied to. So if we want the resulting distribution, like p of x, to normalize to 1, just like the original distribution p of z, we need to account for this volume rescaling factor. So let's see what is the change of variable formula by an example. Consider z to be a uniform random variable between 0 and 2 with its density pz. So the question is, what is the probability of observing 1? Since we know z is uniformly distributed and the sum of probabilities within this bound should be 1, then we know that p of z equals 1 is 0.5. So now consider that we have another random variable x that is a linear transformation of z, say 2 times z, and px is its density. In this case, the question is, what is the probability of observing x equal 2? So one might come up with this solution, that px of 2 is equals to the probability of observing x equal 2, and we know this linear transformation. So we can say 2z equals 2, which means z equals 1. From the first example, we said p of z equal 1 is 0.5, so the the probability of observing x equal 2 is 0.5. Can we do this? Absolutely not. Because we didn't consider the fact that px is also a probability density, so the sum of probabilities within its bound, which is from 0 to 4, because it's 2 times z, should be 1. So p of observing x equal 2 is 0.25. And this is exactly what change of variable formula takes into account, that a transformation from one distribution to another should preserve the probability mass. So change of variable in one dimension basically says if x is the transformation of z and f is an invertible function, we can go back from x to z using the inverse of f, that is, we call it hx. Then the probability of x is simply the probability of h of x under the prior distribution multiplied by the absolute value of the derivative of h of x. And using this formula, we can answer the second example pretty easy. So it's fairly straightforward to extend it to 2-dimension and later to n-dimensional space. So let's z to be a uniform random vector shown in the unit size blue square. It's clear that translation as a transformation does not affect the area, or if you consider n-dimensional case, the volume. So everything should be fine with translation as an invertible transformation. On the other hand, a more complex transformation like A in this form can transform the unit square that we call Z to a parallelogram that is, or X, this one. If the transformation is in this form, then the area of the parallelogram is simply AD minus BC. And since we observed that the translation does not have any effect on the probability mass, we can safely consider both has been originated at the center. Surprisingly, the area of the parallelogram is same as the determinant of the transformation function. So if we compute the determinant of A, we see that this is AD minus BC, which is the area of this parallelogram. So we call our parallelogram X, which is the transformation of Z through the transformation A, and A is an invertible matrix. Now if we want our X to be also a probability distribution, so we want its probability mass to be preserved through the transformation A, what we should do is to normalize Px by the area of this parallelogram to make sure that the area becomes 1. And that is the absolute value of the determinant of the transformation, because this equals to the area of the parallelogram. This leads to the general definition of the change of variable formula. As we saw in our example, for linear transformation like A, the change in area or volume is given by the determinant of the transformation. We can extend it to nonlinear transformations F, that the change in area or volume is given by the determinant of the Jacobian of the transformation, which I won't go through the detail, but I will share some links if you want to know more details about that. What is important here is to know that both Z and X have the same dimensionality. Moreover, we can replace Z simply by having the F inverse of X. So in some of the computation, it could be useful. And also, we know that for any invertible matrix, the determinant of the inverse of A equals to the inverse of the determinant of A. So we can write the change of variable formula like this. And this is the whole idea of invertible models and normalizing flows in general. So now we can write everything with the parameters theta to show that to show this kind of transformation within a neural network. Now we can come up with the marginal probability of any observation using this form, because we can compute P of X using this. So it's feasible to train such model with maximum likelihood, maximizing this term. Let's see how we can construct a flow-based generative model. In fact, it is not easy to model complex data distribution like this using a single transformation F. In fact, coming up with such transformation that is both invertible and differentiable is not easy. A solution to this is to compose multiple of such transformation to create a complex transformation. So starting from our prior distribution, with each transformation, we add a little bit of complexity such that after composing a number of these transformations, we can model our data distribution. So this is why it's called normalizing flow. It's normalizing because the change of variable formula gives us a normalized density after applying each of these invertible transformations. And it's flow because transformation can be composed together from a very simple distribution to a really complex one. This is another way of showing the composition of transformation. So starting from a simple distribution for Z0, which could be the Gaussian distribution, the normal distribution, we can apply a sequence of M invertible transformation so that the result of the last transformation, Zm, represent our data distribution. Then by change of variable formula, we can write the marginal likelihood of this form, like this, which contains the products of the determinant of the Jacobian of different transformations. So now we have this for a very complex transformation that is a composition of invertible transformations. So how practical it is to implement something like that? From a practical point of view, we need to be able to compute the inverse of F. We need to be able to compute the determinant of its Jacobian because it's appeared in this formulation. And we need to compute their gradients because we want to do maximum likelihood estimation for training. And all of these should be fairly efficient to be able to use it in an iterative process on training on large data sets. But the problem is that in normalizing flow formulation, the Jacobian matrix is an n by n matrix, where n is the data dimension. And computing the determinant in this n by n matrix is very expensive. It requires the order of n3. And this is considerably can slow down the training because we require to compute this determinant of Jacobian over and over during the training. So we need to come up with a solution that computes such determinant in an efficient way. For instance, we know that determinant of a triangular matrix is simply the product of the diagonal entries, so it can be computed linearly with the dimension of the data, say in the order of n. So let's see, what does a triangular Jacobian matrix mean? So we have our observation X, and we can open up X to show it like X1, X2 up to Xn, and we know that this is a transformation of Z. We can open up this transformation to like F1 of Z, F2 of Z, up to Fn of Z. So to make the Jacobian triangular, we need the computation of each xi through the transformation to be dependent on Z up to dimension I. And in this case, for example, F1 only depends on Z1, so the rest of this are 0. F2 only requires seeing Z1 and Z2, so the rest of that becomes 0, and so on. So which makes the Jacobian matrix a triangular one. In the literature, there are many flow-based generative models that utilize such formulation of the Jacobian matrix, like these and with a growing list. And what is important in all of these methods is that we need to look for two things. First, both forward and inverse mapping should be efficient, and the determinant of the Jacobian should be tractable to compute. I'm not sure how much time I do have, but I would like to go fast through the NICE approach, which is nonlinear independent component estimation. So similar to what we've already discussed, NICE uses the composition of multiple transformations. Each transformation from Z to X, or to be more precise, from Zi to Zi plus 1, is something they call affine coupling layer. The idea is pretty simple. NICE partitions the latent variable Z into two subsets, say Z from index 1 to D and the rest of the Z from D plus 1 to N. The transformation in the forward mapping on the first part is simply the identity mapping. So X for the first part is equals to Z for the first part. The transformation on the second part is utilizing a function M, which could be a neural network, on the first part that is added to the second part. And the inverse mapping is pretty similar to that, but instead of having addition, we have subtraction. Note that to compute the inverse mapping, there is no need to compute the inverse of M, so we are flexible to choose any architecture for M. Given such forward mapping, we can compute the Jacobian of the forward mapping pretty easily because the elements in the diagonal are going to be identity. Because look at the derivative of each of these two parts with respect to Z in that part. In that case, it is always identity, and so the determinant of the Jacobian is always 1. This is also called volume preserving transformation because the determinant of the Jacobian, which accounts for the change in volume, is always 1. And with this simple architecture, we can generate data points on, for example, faces or digits. And if we want more expressive transformation functions, there are more advanced normalizing flows like GLOW that you can take a look at the paper. Now let's take a look at a code of implementing VAEs for image generation really quickly. So the architecture is pretty simple. It is just fully connected layers for MNIST digits. We have an encoder that maps the data dimension to some embedding representation. Then we have two layers that represent the parameters of the approximate posterior that when we sample a latent variable from, we map that latent variable to the embedding dimension, and the decoder gets that as input and reconstruct the data. In the forward pass, similar to what we saw earlier, we use the encoder, and the input is going to be our data. The encoder provides us with the parameters of the approximate posterior. Then we sample from approximate posterior Z, and then we use Z as the input to the decoder. And it's done by this. Like in the encoder here, we return the parameters of the approximate posterior. We use the reparameterization trick to sample from that, and we pass that to the decoder to generate the data. The training follows the very standard training pipeline of almost any neural network, but the loss function here is important. Since we saw that we want to maximize elbow, the loss function is going to be negative elbow, which is the combination of the reconstruction loss and the KL divergence between the approximate posterior and the prior distribution. Once we've trained the model, we can ignore the encoder, and we can sample from the prior distribution, which is just a normal distribution, and we can pass that latent variable to the decoder to generate the data. And this is, for example, the output of such simple, fully connected model, and these are novel digits that has been generated from this model. As we said, we can also use VAEs for explaining the data in lower dimension. So if we consider the latent dimension in 2D instead of 2NE in the example we saw, it is fairly straightforward to have such data representation, how different classes are organized in the latent space, or we can analyze the values of different dimensions of the latent space to know more about the properties of the data. And if we want to do the same with higher dimension of latent variables, we can use dimensionality reduction such as TSNE to visualize the latent space in 2D or 3D. So to summarize, we learned about latent variable models. We talked about why these are important. Then we discussed two latent variable generative models, VAEs, which we need to approximate inference, but we can use any expressive model. And we also saw normalizing flows that allows us to use exact inference. And we looked into a simple implementation of VAE for image generation. To prepare this material, I used different references like the paper of Nice, the Kingma PhD thesis, which is the author of Variational Autoencoder, and the Stanford course and the DeepMind's deep learning lectures. Thank you.